developments in quantum circuit.
Hi everyone. Yeah, thanks, Joe and Tian. Yeah, thanks for inviting me to come speak here. It's always fun. So yeah, I'm going to tell you about some recent developments in this kind of new area of quantum circuit complexity. I mean, circuit complexity is one of the most important sub areas of complexity theory, but in the quantum realm, it hasn't been explored as much, and so this talk will sort of try to give you an overview of some of the things that we know, which is very little, and mostly focus on a lot of the open problems that we have. Okay, and also please feel free to ask questions. Like I'd be very happy to make this interactive. Okay, so just to start off with, let me first set the stage by talking about a little bit of what we know in classical circuit complexity. And like I mentioned, finding explicit circuit lower bounds is one of the holy grails of theoretical computer science, complexity theory. And there's been some wonderful successes in the field. And just to give an incomplete list of highlights, I mean, even from the very beginning days of information theory, from Shannon, that if you pick a random function with high probability, it will require exponential size circuits. So these hard functions are definitely out there. And of course, we're very interested in identifying an explicit one. And over the decades, we've had some these wonderful celebrated results. Like in the 80s, we were able to prove that parity is not computable by something called AC0 circuits, which I'll talk about in a little bit. Then people were able to prove that parity is not contained in a slightly more complicated class called AC0, augmented with mod P gates. And then things kind of got stuck for a while. And then about 15 years ago, Ryan Williams proved that non-deterministic exponential time cannot be solved by ACC0 circuits. And I won't go into the precise definitions of these classes just yet, but this is sort of progress. There's been lots of other types of progress in restricted classes of circuits, like monotone circuits, algebraic circuits, tension programs, and so on. And really, I think one of the reasons we cherish these results is because in proving them, we had to introduce lots of interesting and deep techniques analyzing circuits and complexity. So restrictions, polynomial methods, algorithmic methods. Okay, so from one point of view, it sounds we've been as a field we've been doing some very interesting work. We've been doing a good job, but it's also not so hard to take the other view in which we've had a lot of failure in this area. Right? So, for example, we still don't know how to prove that depth-4 neural networks, or more formally TC0 circuits, which is a very restricted class of computation. These are constant depth circuits with majority gates. We don't know yet how to prove that these circuits can't compute all functions in non-deterministic exponential, beyond what we know how to do in theory. We also don't know how to prove that NP requires circuits bigger than n to the 1.00001. And due to the stalling in progress, we've also turned to trying to identify the reasons for why we've been having. And we've identified some barriers. So we know that there are limitations to proof techniques in proving circuit lower bounds. You can't prove strong circuit lower bounds or complexity class separations using relativizing proofs, natural proofs, or these things called algebraizing proofs. All right, so that's kind of in a nutshell where we're at in terms of successes. A lot of hard problems are floating around and very barriers to get around. Okay, so what about the quantum setting? So just to get us all on the same page, because I know not necessarily everyone has a quantum background, let me give you a quick crash course in information. So in the quantum setting, a quantum state on n qubits, sort of quantum analog of bits, it's represented by a 2 to the n dimensional complex unit vector. And you can think of it as analogous to a probability distribution of bit strength. Except these probabilities can be not just positive numbers, but they can be negative or even complex numbers. And a quantum computation is going to be a sequence of unitary transformations on these states, unitary transformations and measurements. So what are these two types of transformation? So unitary matrices are reversible state transformations. So if you apply unitary transformation, you can always apply the inverse. And this is analogous to applying a doubly stochastic matrix in probability theory. Right? So we know that doubly stochastic matrices map probability distributions to probability distributions. Invertible. So unitary matrices are the quantum analog of that. The other type of transformation that can happen to a quantum state is measurement. This is a non-reversible state transformation. And when you take a measurement of a quantum state, you actually get a classical probability distribution. But this has the effect of, it's non-reversible unless you convert a quantum state to a classical probability distribution. So that's the setup of quantum information. Now let me talk about quantum circuits. So how do we actually realize these transformations in the real world? And so, if we wanted to run a quantum computation on n qubits, so we could, you have these n particles representing your quantum bits. And you can compute on these quantum bits by applying a sequence of gates. So you can apply either, let's say, single qubit gates or 2 qubit gates. These 2 qubit gates will, so time goes from left to right, and this gate will act on, let's say, the first 2 qubits. This gate will act on the third and fourth, and so on. And you just apply the sequence of gates. And for now, I'm just going to only think about unitary transformation throughout this talk. I won't worry about measurements so much. And mathematically, each qubit gate is, if it acts on k qubits, it's represented by 2 to the k by 2 to the k matrix. And if you have such a quantum circuit, then there's different complexity measures you can think about. So one is the depth of the circuit, which is the number of layers of gates in the circuit. And so in a layer, we can apply all the gates simultaneously, parallel. And you can organize your circuit into these layers. So that's the number of layers of the depth. Size of the circuit is the number. And overall, this entire sequence of gates corresponds to one giant unitary transformation on these n qubits. So if you multiply all these unitaries together, so in a layer, you can take the tensor product of these unitaries, and across the layers, you can multiply the unitaries, and at the end, you'll have a 2 to the n by 2 to the n matrix. Very complicated stuff. That's the model of quantum circuits. So every n qubit unitary transformation, so you can think of this giant transformation here, can always be broken down into a sequence of single qubit. And in fact, we just have to focus on a specific 2 qubit gate called the C-dot gate. And in general, any unitary can be broken down into a sequence of at most 4 to the n gates. And we know by a counting argument, similar to Shannon's counting argument that almost all functions require exponential size circuits, so too, almost all unitary transformations require exponential size quantum circuits. Break it down into the and what sort of single qubit gates are allowed? In general, we fix some universal discrete gate set. There's a finite gate set that you can approximate any, out of these finite gates, you can approximate any n qubit arbitrarily. Any questions about this? Okay, so what do we know about quantum circuit complexity? And there's also been a few successes, some nice positive results. So, like I said, just by a dimension counting argument, we can argue that nearly all unitary transformations require exponential size. We actually know we can identify an explicit unitary that requires exponential size quantum circuits. We can write down the entries of this unitary. We can prove that any quantum circuit that implements it requires exponential size. That is, if you want to implement the unitary exactly. So it's not a robust statement, meaning that for all we know, this particular explicit unitary, if you want to approximately compute it, maybe there's a polynomial size. In fact, I think for this specific unitary, that's known. Oh, this unitary. So here we're no longer talking about computing the find one of these unitary transformations. Doubly stochastic. On the computer, how many gates does your quantum? So at least so far, we're not talking about computing quantum transformation. But later in the talk, I'll talk about. So here, explicit means that in polynomial time, I can tell you every entry. So I'll say maybe one word about how this is proved. I mean, this is kind of interesting because we don't have an analog of this result classically. Proved quantum setting. Right? It's not about computing some moving function, but again, but the way they prove it is using some very how should I say it? They use methods from number theory. So they construct this unitary matrix. Somehow they like construct it in a way that each the entries of this matrix are like these certain kinds of non-algebraic numbers, and they show that because of these particular number theoretic properties of entries, there's no way to in polynomial size circuit or even sub-exponential size circuit. So I think there's I don't remember the details, but there's some. You can specify the precision. 8-digit. Yeah, it's not. I mean, you're not outputting the number, but in some sense, the Turing machine that. I see. But here, the gate sets in this lower bound, they're allowing the gate sets. So we know. Yeah, it's. I mean, it's. That's. It's interesting, but not. Yeah, what do we know about it? So quantum circuits, it's a non model, right? Like family of circuits that size and insist that possible Turing machine. That would be this uniform circuits can also be simulated. Model. So this was from a couple of years ago. And we also know of something called the light cone argument, which I'll explain in a second, for proving lower bounds against shallow quantum circuits. So this is, in some sense, these are kind of like the successes that are known, at least broadly speaking, in quantum circuit complexity. What about the failures? Well, I'd say the field is a bit too young to have failures yet. So there's some very interesting questions. Oh, good. So I'll talk about it right now. So what do I mean by shallow quantum circuits? This will sort of be the main setting for the rest of this talk. So generally, shallow just means vaguely, we're interested in circuits where the depth of the circuit, the number of layers, will be much smaller than the number of qubits. And particularly, we can be interested in families of constant depth circuits. So that's represented by the circuit class QNC0, quantum analog of NC0. Classical circuit. These are families of circuits where the depth is independent of n. So here, these are really families of circuits where the circuits act on more and more qubits, but the depth is always fixed. And people are very interested in this model of shallow depth circuits or constant depth circuits these days. A very useful model of near-term quantum computing. Current-day quantum computers that we have. People build quantum computers. They oftentimes look something like this, and but they're very noisy. So really, we should think of them as being capable of executing a few layers of gates before the noise overwhelms the system. These machines that people are spending billions of dollars to build are executing these. So good. Exactly. So in the types of machines that people are building today, although people are starting to explore, the gates act on at most 2 qubits. I mean, there's some experimentalists who try to have like 3 qubit gates. That's like extremely difficult. Having gates that act on sort of growing numbers of qubits. If you mention that to an experimentalist, they'll laugh you out of the room. Because it's just very, even getting them to have a gate that acts on 3 qubits. I'm not an experiment. Physics stuff, yeah, physics typically. I have utmost respect for what they do. It's very, so yeah, people are very interested in understanding what is the power of these shallow depth quantum circuits. What are their limitations? And theoretically, we know some things about them. So in one sense, even though these circuits are very shallow, they're still capable of doing very interesting things. So we know that QNC0 circuits, these constant circuits, can generate probability distributions that cannot be sampled efficiently on a clock, which is very cool. So we have results being after 2003, and you can set up these circuits and under plausible complexity assumptions like polynomial hierarchy not collapsing, the output distribution, meaning that if let's say you started all your qubits in the 0 state, and you ran this constant depth circuit, and then you just measured each of these qubits in the end, you'll get an n-bit string sampled from some distribution. That distribution should be hard for a classical computer. That's also true for 1D. 1D meaning that like your gates act on like the nearest. So yeah. So that's conjecture to be true. It's not proved yet. Okay, people have proved that sampling this from a very, very small approximation. Proving it that sampling from such circuits in constant variation part is believed to be true. Other like yeah, so circuits are capable of generating classically difficult probability distributions, but on the other hand, they are still very weak. For example, we know that such constant depth circuits cannot prepare states or even probability distributions with what are called long-range correlations. If you start with an unentangled input state, so you start your qubits all in the zero state, you cannot generate a state that looks like the equal superposition of the all zero state and the all one state. State is very special in quantum information. The zeros as representing the state of a cavity alive, and all ones as the state. And actually, I'll give you a proof of why this is the case. And this uses the light cone argument, which is the title of my talk. So what is the light cone argument? It's roughly this, very intuitive idea that if you look at any output qubit of a shallow depth circuit, the number of gates that are like connected to it is small. So in a depth-D circuit, if you only have gates that act on 2 qubits at a time, there can be at most 2 to the D gates that connected to it. Right? So like this gate in some sense is never involved with computation. And if D is constant, then 2 to the D is also constant, small number. And so using this observation, how do we prove that, let's say, the cat state cannot be prepared by constant depth circuits? Well, you say, in the cat state, suppose I looked at, the marginal state of any 2. Like I took 2 qubits in the cat state and I just measured it. And, just believe me when I say that you're going to get an equal mixture of 0, 0, and 1, 1. Probability half you get 0, 0, probability half you get 1, 1. So the measurement results of these 2 qubits, no matter which 2 qubits you pick, are always going to be perfectly correlated. But on the other hand, you can also show that if you have 2 output qubits of a QNC0 circuit with disjoint light cones, the state of those 2 qubits must be uncorrelated. Because in some sense, if their light cones don't intersect, then there's no way for the circuit to coordinate the behavior. So therefore, QNC0 circuits cannot compare. I guess whether you call it forwards or backwards, it depends on orientation, but yeah. You can also talk about light cones of input. Any questions about the light cone argument? It's pretty intuitive, very simple. So despite being so simple and intuitive, essentially this is the only trick in the book that we have for proving quantum circuit lower bounds, essentially. It's simple, but people have been able to get a lot of mileage out of it together. All right, so now let me tell you a bit about, aside from, just interest from complexity theory, why are people from physics and other areas of theoretical computer science interested in quantum circuit? I'll give you sort of 3 interesting connections. So here I'm just sort of telling you about interesting things. So the first is something known as the quantum PCP. And in classical theoretical computer science, one of the crown jewels is something known as the classical PCP theorem, which says that not only is it NP hard to solve a lot of constraint satisfaction problems exactly, it's NP hard even to find approximate solutions, even up to constant fraction error. Wonderful result, lots of downstream consequences of this theorem. In quantum complexity theory, there's a big open question of whether there's a quantum analog called the quantum PCP conjecture. And what it states is that it is QMA hard. So QMA is some quantum analog of NP, where classical proof that's efficiently checkable. Quantum proof. It is QMA hard to approximate the lowest energy of something called local Hamiltonians are just quantum analogs of. It says that it's QMA hard to do so even up to constant fraction. This is a conjecture. We don't know that this is true yet. Actually, we're kind of split on whether it's true or not. But it's a very interesting conjecture that have gotten physicists quite interested because it actually has some implications about natural physical quantum systems. So, and the reason for that is because if you make some plausible complexity assumptions, the quantum PCP conjecture implies that what are called low energy states of local Hamiltonians. So in physics, local Hamiltonians are what you use to describe quantum physical systems. So they're saying that there exist quantum physical systems where even at not necessarily like zero temperature, but non-zero temperature, you can have like the quantum states of these systems have high quantum circuitry, which would indicate that you're seeing some very strange quantum phenomena in these systems. And let me actually just say a little more about this implication. So if you assume this quantum PCP conjecture, and also this complexity assumption that the quantum analog of NP is actually distinct from the classical NP, then this tells you that low energy states of local Hamiltonians cannot be prepared by these. So this is a known consequence of QMA not equals to NP. And in fact, this conclusion that you can construct these quantum systems where even these low energy states cannot be prepared by constant depth quantum circuits. This wasn't known, and so it was raised as a conjecture. Some other conjecture known as the NLTS conjecture. This was very interesting in like the condensed matter physics community, and only a couple of years ago it was unconditionally proved. So it wasn't proved by settling the quantum PCP conjecture, but they just outright wrote down a system of Hamiltonians and showed that these low energy states are verified. We can make a stronger statement still. Say that if you assume this quantum PCP conjecture and something known as QMA is different from QCMA, and maybe I won't go into what QCMA is, but you have a classical proof verified by a quantum computer, then this tells you that not only can you have quantum systems where the low energy states cannot be prepared by constant depth circuits, but they can be prepared by any polynomial size circuit. Really the kind of the takeaway interpretation of what this means is that it is possible at room temperature, states that have highly complicated that cannot be described. And again, we don't know that this is such local Hamiltonian exists. A lot of physicists actually believe that they don't exist based on their physical what they know about quantum systems. But this is sort of the consequence. And kind of the thing I want to point out here is that really this is a question about quantum circuitry. Saying that you're sort of, if you want to prove that this is true, then you have to establish that some states cannot be prepared by polynomial size circuits. Run up against So that's about a connection to quantum PCP. Here's another reason that physicists are interested. Again, comes from something like physics. The important goal of this area of physics is to classify what are called quantum phases of matter. And we're all familiar with phases of matter like solid, liquid, gas, right? And but in condensed matter physics, people are also interested in what's called quantum phases, which are talking about how depending on different global parameters of the system, like you can have different patterns of quantum correlation between particles. And for example, like people believe that superconductors are, the reason that superconductors exist is because sort of the behavior of electrons in such materials belong to a certain quantum phase of matter. And unlike classical physics, where there's just like 3 phases of matter, in quantum physics there's like a whole zoo of different quantum phases of matter. And so since the 70s and 80s, people have been interested in classifying these. The modern quantum information perspective on this is that the way you define a quantum phase of matter is that it's really an equivalence class of states connected by constant depth quantum circuits. So when a physicist tells you that they've proved that 2 states are in different phases of matter, what they're implicitly saying is that they've proved quantum circuit. So this also comes up. Okay, so maybe I'll skip over this one, but also people in the black holes quantum gravity community are also very, very interested in quantum circuit complexity, and somehow they have these very interesting conjectures about the quantum circuit complexity of random quantum circuits. Let me tell you about the frontier, some recent work that I've been involved with. And so, the light cone argument has been successful at proving limitations of constant depth quantum circuits. But we want to sort of move beyond that, right? Can we prove lower bounds on stronger models of quantum circuits? So, let's sort of take baby steps. What if we augment these shallow circuits, these constant depth circuits, with gates that don't just act on 2 qubits, but gates that act on, say, many qubits, a growing number of qubits? And here, the light cone argument no longer works, because now, even if you have a single long, many qubit gate, now the qubit could be correlated with many input qubits. You can't use light cone arguments anymore. And now we've run out of tricks. How do we prove lower bounds in this setting? And it's interesting because the answer will depend on what kind of many qubit gates. So actually, way back in 1999, Christopher Moore proposed 2 such models of quantum circuits, QAC0 and QAC0 subscript F. So that F will stand for fan out. I'll say more about what these circuit models are. And he defined these as 2 quantum analogs of the classical circuit model AC0, which, if you remember from the very first slide, represents like one of these highlights of classical circuit. What is classical AC0? Just as a reminder from complexity class. So this is a model of constant depth polynomial size circuits where we have AND or NOT gates with unbounded fan. So that's the key thing about the circuit model, is that each gate can talk to as many other gates as you want. And the main restriction is that the number of layers of gates you allow in the circuit is common. But you also notice that, and even classically here, this circuit model is not so easy to reason about because of that advantage. But we have classical lower bounds against this class. So therefore, it means that we must have, at least in the classical setting, been able to develop techniques beyond light cones. Again, we know that the parity function cannot be computed. So what is QAC0? What's a quantum analog? So Chris Moore defined QAC0 with what are called Toffoli gates. So this is the many qubit gate that I'm going to talk about. They're constant depth circuits. I'm going to allow you arbitrary single qubit. They're just 2 by 2, arbitrary 2 by 2 unitary matrices. And the many qubit gate that I have is this Toffoli gate, which you can just think of it as a reversible AND gate. So it takes in many input bits, so x1 up to xk, and there's a target bit b, and it's what this gate is going to do is going to just flip the target bit, this very last bit, depending on the AND of the first k bit. So in quantum circuit notation, you have these control bits, and they'll flip the target bit depending on what the That's the Toffoli gate. And here's a picture of a quantum AC0 circuit. You have your single qubit gates in this first layer. And then in this middle layer, I'm going to apply a giant Toffoli gate that acts on all qubits. And then maybe I'll apply a smattering of single qubits. You can see that the Likman argument doesn't work because let's say that this output qubit is connected to all the input qubits through this long range. So this is QAC0. Now, what is QAC0 subscript F? So this is where I change this multi-qubit gate. Instead of Toffoli, I'm going to give you the ability to apply what's called a fan-out gate. So it looks very similar, except what it does is it takes this first bit and just flips all the other bits based on x. It'll flip b1, for x into b1 and x into b. So think of it as it's just kind of like a gate that copies this single bit into many target qubits. Maybe this seems like this is actually not a valid quantum gate because it's not allowed to copy quantum information. But the important thing is that all the copying is done in the classical. So this is another model, QAC0 with that.
QAC0.
Good. Okay, so the Yashin's question is like, why are these natural analogs in AC0? So here it kind of makes sense because you have unbounded AND gates, just like the other classical AC. Here, but you also have fan out in classical AC0 in the sense that something I didn't mention is that you're allowed to copy the input bits as many times as you want. That's actually very important. X1 can appear here, not X1. Quantumly, copying is not such a natural, not allowed to copy quantum information. But here we're going to give you some ability to copy. So you can copy the classical basis. That's what this gate is. All right, 2 different models. Okay, what can we say about them? So what's interesting, first thing is that fan-out gate can simulate Toffoli gates. What that means is QAC0 with Toffoli can be simulated or just contained in the class QAC0 with that. And the key questions is, well, still, what are the relations? First of all, what can be computed in these 2 classes? And are they different? Or are they the same power? Can they compute with things, or is QAC0 with fan-out actually strictly more powerful? Let's talk about QAC0 with fan-out. And the punchline is that it's actually a surprisingly powerful fan-out gate. Really makes all the difference. First of all, we know that the parity function is actually computable in QAC0 with fan-out. And actually, there's a very simple circuit to do so. If you want to compute the parity on, let's say, a bunch of input bits and save the parity into the last bit, you can do so by applying a bunch of single qubit gates known as Hadamard gates in the beginning, apply a fan out, and then apply another column of Hadamard gates. Step 2, on the size, you can compute. So even though that this is a possible, a reasonable analog of classical AC0, you already see some difference. No parity cannot be computed by classical AC0, fan out, and the quantum setting. What else do we know? We know that the fan-out gate is equivalent to preparing these cat states, right? Globally entangled, globally correlated states. It's a very simple circuit. Hadamard, that puts this qubit in 1, and then you just kind of spread that superposition to all other qubits. Zeros plus. We also know the reverse. If you're able to prepare the cat state, let's say in constant depth, then you can actually compute the parity function in constant depth. And yeah, so in fact, all 3 of these operations are equivalent to constant depth. Computing fan out, preparing the cat state, and computing parity are all equivalent. That's something that's interesting. And actually, even more is known. So there's a very nice paper from 2005 that says quantum fan out is powerful. And they showed a whole bunch of things that are computable in constant depth if you have access to this fan out gate. 2 gates, the majority function, you can form the quantum Fourier transform, all sorts of arithmetic operations. And so it's a very powerful class. Yeah, so good. So it's known classically that even if I give you, the AC0 circuit, then I throw in the parity gate, still can't compute sums of bits mod 3. But in this quantum case, you can, with a parity gate or a fan-out gate, you can compute mod 2 gates for it. And so, for the complexity theorists here, so this implies that, for example, QAC0 with fan-out can compute anything in the class TC0, which I mentioned we don't have any explicit lower bounds for. Very, very powerful class. Yeah, so again, just returning to this open question, what is the relationship between these 2 different analogs of AC0? And the Toffoli gate alone compute fan-out or parity QFT. We don't know. This is a conjecture. We conjecture that they're different. And I'm sorry. I meant that. Yeah, Toffoli gates was similar. Yeah. Yeah. So this question was actually raised 25 years ago in Chris Moore's original paper when he defined these 2 classes. Are these 2 classes equal? It's been 25 years, and we seem to be, we don't know the answer. And there's been modest progress. In the early days, it was proved that if you have QAC0 with sublinear ancillas, what does ancillas mean? It means like the number of workspace qubits that aren't part of your input. Use them for scratch space. The number of ancillas is sublinear. You can't compute parity. It's known that depth 2 QAC0 circuits can't compute parity. And a couple of years ago, my student Greg Rosenthal showed that there are constant depth circuits, QAC0 circuits approximating parity, but they are exponential. Even showing an exponential size construction. So let me talk about an approach that we took recently. This is to take a spectral approach. So we'll take some inspiration from what people have done in classical complexity, and that is to look at the Fourier spectrum of functions that you're interested in. So if you have a Boolean function f, you written as a Fourier expansion in this way. You have these Fourier coefficients, you have these characters. The Fourier spectrum of a Boolean function encodes extremely useful information about complexity. So here's one of the really nice theorems back in the early 90s by Lineal Mansour Nissan. And it says that if you have a Boolean function that's computable by a depth D, size S, classical AC0 circuit, then there's something very nice about its Fourier spectrum. It essentially concentrates on all the low degree coefficients. And so if you sum up the squares of all the Fourier coefficients for all the coefficients where the degree is, let's say, above k, like the size of the subset is above k, then you have something that's exponentially decaying with the level of k. It depends on the size of your circuit and the depth. But you have some kind of exponential decay. And so there's a really nice picture to have in mind, which is that AC0 circuits compute Boolean functions whose Fourier spectrum kind of looks like this. Plotting like the level here, k goes between 0 and n. And most of the mass of the Fourier spectrum is going to be concentrated at levels that are below polynomial. So from this nice theorem, you'll automatically get a lot of nice consequences. Like you can just proof by picture see that AC0 circuits cannot compute the parity function because of the Fourier expansion of the parity function is just a single point at n, level n. So that's clearly not the same shape, so AC0 circuits can't. Very, very nice theorem, and yeah, there's consequence in the lower bound, let's say a parity function, or any other function that doesn't have this Fourier concentration. Get some nice consequences about pseudo-randomness. So, for example, AC0 functions cannot be pseudo-random. Easily distinguish them. And relatedly, that also means that they can be learned in quasi-polynomials. You have an algorithm that just tries to learn all the Fourier coefficients up to the level polylog n, and you'll have a pretty good. So wonderful theorem, wonderful consequences. And we try to mimic some of its success. Is there a quantum analog of this Nissan theorem for quantum circuits? So we try to do that. So this is in joint work with Michelle and my colleague who's at MIT now, my student RM, and Francisco Vasconcelos, who's at Berkeley. We introduce a quantum analog of the Fourier spectrum of quantum circuit called the poly spectrum. And result number one is we show that the poly spectrum, when you define it in the right way, the poly spectrum of a QAC0 circuit with some conditions, Yuen Silas, and I'll say more about that in a second. It also has a nice spectral concentration. That's nice. And as a corollary, or again, just using the same proof by picture, this already tells us that QAC0 circuits with Yuen Silas cannot approximate parity. And we also get a learning theory result. Quantum circuits with a concentrated polyspectrum can be learned central efficient. So let me explain what this poly spectrum is. So here's a quick linear algebra review. In quantum information, there's some very important single qubit poly matrices, called the poly matrices. So there's you have an identity matrix 1, 0, 0, 1, the X matrix 0, 0, Y matrix, and the Z matrix. These are all unitary matrices, so they're like single qubit. I can combine them together by taking tensor products to get what are called n qubit poly matrices. Take like, for example, X tensor Y, tensor I, tensor combination there. So there's 4 to the n of these n-qubit Pauli matrices. Very nice fact that every n-qubit matrix, it doesn't have to be unitary, it doesn't have to be symmetric or anything. Every n-qubit matrix, so this is a 2 to the n by 2 to the n matrix, can be written as a linear combination of n. You have your sum over these 4 to the n possible Pauli strings. You have some coefficient, alpha sub p. And you have these tensor products of these elementary. You should think of this as the analog of the Fourier expansion. Okay, so how do we define the Pauli expansion of a circuit? So let's say you have a circuit C as n input qubits, A ancilla qubits, that's the number of workspace qubits you use. And this is kind of the key thing that you have to realize, that we want to focus on circuits that have a single output qubit. So circuits in general, like what are the number of qubits that come in or the number of qubits that come in. But we're interested in ones where we only want to measure the first qubit of the output because we're just interested in the yes or no answer. Very different. So if you have such a circuit, we're going to define this matrix. So the following diagram defines an n-qubit matrix. So you have your circuit C, and let's imagine that these 3 wires correspond to the n input qubits, and these last remaining wires correspond to the ancilla. These are the ones that you initialize to zeros. So as a matrix, so this is an n plus a qubit matrix. But I'll do this thing where I'll take this matrix, multiply some of the, stick in zeros for the ancilla qubits, because that's what we initialize it as. Apply the Z matrix to the first wire, and apply the inverse of your, then sandwich it with these zeros in the end. This doesn't make sense to you, don't worry. The point is that this is a diagram that indicates an n-qubit matrix. N qubits because there's n input wires that come in and input wires that come out. So I'm going to call this matrix phi sub c. This is the thing that I'm going to analyze. So the Pauli spectrum of this circuit is going to be the Pauli decomposition of this matrix. Remember, I just said every n-qubit matrix can be decomposed. These alpha sub p's are going to be the Pauli spectrum. And it's a nice exercise to show that if you define things in this way, these coefficients behave very similarly to Fourier coefficients. Sums of squares sum up to 1. All these p's are orthogonal to each other in a certain way. So, yeah. Very nice, has lots of nice properties. And this is what we proved about the spectrum. If you had a circuit that was computable by a depth d size s QAC0 circuit with A ancilla qubits, you also get this spectral concentration. It should look pretty similar, but with a few differences. So again, what is this weight? You take the sums of squares of Pauli coefficients, 3 greater than k. This part should resemble, classical LNN. You get this exponential decay in the level. What is this 2 to the a doing? This is why we have this restriction. Some unfortunate exponential dependence on it. If you use lots of workspace qubits, this kind of blows up this quantity and gives you okay, but we have some, now that we have some quantum analog of LMN, I'll talk about projection in a second. Yeah, we don't think it should be there. I think it's just a limitation of it. So yeah, we get these similar consequences like in the classical setting. If you have these QAC0 circuits with little o of n to the 1 over d ancilla qubits, where d such circuits cannot approximate parity or majority function. You get a learning theory result, except the poly-sized QAC0 circuits with log n ancilla qubits. Can be learned in quasi-polynomial time. We can get some circuit lore bounds here, although with big caveat being that we're assuming that the workspace of these circuits is not so large. Very, very quick overview of how we prove this low degree concentration. So just for simplicity, let's assume that the number of instances is 0. And so we start off with an n qubit size SDF circuit. And what we're going to do is, really the difficulty of analyzing these things are these long range gates, multi-qubit Hoffman gates. So what we're going to do is we're just going to look at the ones that have arity that are large. Let me say it this way. If your circuit has Toffoli gates that don't act on too many qubits, so let's say the number of qubits that they act on is at most k, then you can show the Pauli spectrum of the circuit has degree at most k. Now, if your circuit has Toffoli gates with arity bigger than this k to the 1 over d, I'll just delete them. I'll literally take my circuit and just remove these large Toffoli gates. And what we show is that this doesn't change the Pauli spectrum of the circuit. So that kind of means that your circuit is not too far from a circuit where the Toffoli gates are not too large. And once they're not too large, you can essentially apply like and then when you introduce ancillas, you sort of run through the math, and when we analyzed it, when you delete these Toffoli gates, it's an extra 2 to the a factor. So that's what we know. This is one question. Do we think that this ancilla dependence should be there? We conjecture it shouldn't. We think that there should be a bona fide, true analog of quantum LMN, where the spectral concentration only depends on the size of your circuit. Shouldn't care about the number of ancillas. If you prove this, then you would have settled this 25-year-old question about whether QAC0. Let me talk about a couple interesting new developments. So one is that, so remember I said classically AC0 circuits are not pseudorandom. Not quite true with QAC0 circuits. Sort of upcoming work with Ben Proxman and Natalie Parham, we can show that quasi-polynomial sized QAC0 circuits can compute weak pseudorandom unitaries. Pseudorandom unitaries are like the quantum analog of pseudorandom. What does the weak mean here? It means that you get security only if you query the pseudorandom unitary in the full expression. Contrast, you know that there's no similar statement. There's and then finally, there's a lower bound that recently came out by Andrew Bone that actually does better than us in terms of the number of ancillas. They show that parity cannot be computed by polynomial-sized QAC0 circuits with a number of ancillas that's fairly superlinear. So if you have a depth D circuit and the number of ancillas is at most n to the 1 plus E, that can be parity. And they prove it using some kind of similar low degree concentration theorem, but it's with respect to the what's I find really interesting about the result is that they show, suppose you could prove a lower bound that's like better than this, so n to the 1.1. That would be enough. You could bootstrap that result to this. So somehow this is kind of, I don't know, somehow they hit upon like threshold. That. But yeah, that's sort of a reason. So wrap up. Summary, we prove a concentration bound for these cases. And there's so lineal, now so Nissan, essentially what they show is that AC0 functions approximately low degree polynomials. And Shimon came up with this, and it's like, and I can't resist. We can think of quantum LMN as saying that QAC0 functions at low degree polynomials. And yeah, so we get the future directions. Number one, let's try to prove the quantum element. Really nice. It probably requires some really interesting new techniques. I don't know, some people suggested maybe there's a quantum version of random restrictions or switching lemma. It's not clear that that's actually needed, but new techniques are nice. Or prove parity not in QAC0 some other way, along the ways of this recent result. More broadly, QAC0 is interesting, but also it's just one choice of, one baby step beyond constant F circuits. There's other models that you can try to do. It's more tractable to prove lower bounds of this. So my student Natalie actually, along these lines, recently magic hierarchy, that it's a hierarchy of circuit models that interpolate between QNC0 and QNC0. And she proved some interesting new lower bounds of this hierarchy. So there are new techniques and new things to try beyond just focusing on. And yeah, more also, the physicists are very, very interested in quantum circuit lower bounds, whether they know it or not. So it'd be nice to find more. Question about polyspectrum of states rather than circuits. Yeah, that's an interesting question. So you can ask, like, if you take the quantum state and is there some notion of polyspectrum that tells you something about it? We tried it for a bit, and actually sort of along these lines. So a lot of this way of defining things is tailored towards showing that like, Boolean function, this parity function, cannot be like QAC0. But it doesn't directly say anything about, like, let's say comparing to cat. Even though I showed you that like parity and cat state and out are all equivalent, but this doesn't directly say anything. Yeah, so it's not so. I mean, the number of z's is important because as you increase the basically, this is just saying I care only about this alpha qubit, and I want to compute a Boolean function. When you want to talk about like all the alpha qubits, then it's not clear that you get any sort of. Like, it's not clear that the polyspectrum of that operator will tell you.